Okay, let's get going here. Now, we've talked about the definition of the integral. Now we're making the distinction between the indefinite integral and the definite integral. An indefinite integral is an integral that has no limits. In other words, we're not taking the area under a curve. We're really doing the antiderivative of a function. So, the integral of f of x dx is capital F of x plus c. Always remember, you need the plus the constant at the end of it whenever there's no limits of integration. And basically what that means is the derivative of capital F is small. Now, one other thing I want to mention here, the word antiderivative that we've thrown in here was just an introductory term for you to understand what an integral is. Basically, we don't use that term anymore. We just call it an integral. So if I want the integral of f of x dx, that's going to be capital F of x plus c. That's my indefinite integral. Now, the definite integral is the area under the curve f of x between a and b, between x equals a and x equals b. And that's going to be capital F of x from a to b, which is capital F of b minus capital F of a, and that's going to be a number. So notice, the indefinite integral is a function. The definite integral is an area or a value. Now, check out page 406, table 1. This is something that you should have etched into your mind. Okay, now, I don't just mean be vaguely familiar with this. I mean have this so that if I walk into your room at 3 in the morning and wake you out of a sound sleep and say, "What's the integral of cosine x dx?" You would just say, sine x plus c. Bam! That's it. Okay, so that's what we have here. We've got the properties. The integral of c times f of x dx is going to be c times the integral of f of x dx. That's just saying you can bring out a constant outside the integral and integrate the function. It also says that the integral of a sum of functions is the sum of the integrals. It also says that the integral of a constant is just going to be that constant times x plus c. And that basically is the power rule in reverse. So when you're integrating x to the n, then you get x to the n plus 1 over n plus 1 plus c. Now notice that only works when n is not negative 1. Because if n is negative 1, then you have the integral of 1 over x, which is natural log absolute value of x plus c. The other thing that I want you to make sure you understand is that it's only the integral of x to the n. That's variable to a power. If you have any other base, like notice the integral of a to the x, that's a constant to a power. That's going to be a to the x over natural log a plus c. Now if we're integrating e to the x, that's going to be e to the x over natural log e. Well, natural log e is just 1, so it's not necessary there. Okay, now the trig functions. You know the integral of sine is negative cosine because the derivative of negative cosine is sine. The integral of cosine is sine because the derivative of sine is cosine. So we really only know the reverse of the derivatives of what we know. Since we know the derivative of tangent is secant squared, then we know the integral of secant squared is tangent. And the integral of cosecant squared is negative cotangent. The integral of secant tangent is secant. The integral of cosecant cotangent is negative cosecant. Now, we don't know the integral of tangent x yet, or the integral of secant x yet, but we will. Okay, then the last things are the inverse trig functions. The integral of 1 over x squared plus 1 is inverse tangent x, and the integral of 1 over 1 minus x squared is inverse sine x. So, like I said, don't just be vaguely familiar with these things. Make sure you know them really well. Okay, cruising onward. Let's do some example problems. All right, so first, we have the integral of 10x to the fourth minus 2 secant squared x dx. Okay, so basically I can take the 10 out in front, and so this becomes x to the fifth, well, 10 x to the fifth over 5 minus 2. Now, integral of secant squared is tangent x. And then we have our plus c, of course. Okay, so this ends up being 2x to the fifth minus 2 tangent x plus c. That's it, game over. Okay, now, let's see. Yeah, that's it. Okay, next one, we have some trig functions. Now, we don't know how to do an integral of a fraction yet. So what we need to do is turn this into something that we do know how to deal with. So notice we've got the integral of, now, cosine over sine. Let's just make this cosine over here's a hint on what we should do. Okay, so now we know that cosine over sine is cotangent, and we know that 1 over sine is cosecant. And so what's the integral of cosecant cotangent? Right, it's negative cosecant plus c, senor. Don't forget that. Okay, so cruising onward. Okay, now we've got a definite integral. Notice the first two examples were indefinite integrals. The solutions were functions. Now, our solution will be numeric values. So, we've got the integral from 0 to 3 of x cubed minus 6x dx. So, this becomes x to the fourth over 4 minus 6 x squared over 2. Now, we don't go plus c, we go from 0 to 3. Now, we can simplify this, so let's just make this, 1/4 x to the fourth minus 3x squared from 0 to 3, and that equals 1/4 times 3 to the fourth minus 3 times 3 squared. Now, minus 1/4 times 0 to the fourth minus 3 times 0 squared, which is 0. So this is going to be it. So we've got 81 over 4, which is 20 and 1/4. Yeah, let's just go 81 over 4. Then minus 27. So how do we want to do this? Okay, let's just make this 4 times 27 And so we've got 108 fourths. So 108, 81, there's 19 and 8, 27 fourths. Okay, so that would be my final answer, 27 fourths. Notice it's a numeric value. Let's see, did we... Whoops, I forgot. 81 minus 108 is a negative 27 fourths. We'll edit that out later. Okay, negative 27 fourths, and that would be your negative 6.75 if we want to put that in decimal. Okay, cruising onward. Another definite integral here. So we integrate each part. So first thing, 2x cubed would be 2 times x to the fourth over 4 minus 6 times x squared over 2 plus, what do we do with that? Oh yeah, it's 3 inverse tangent x. Now, if this was an indefinite integral, I would put plus c at the end, but here I just go from 0 to 2. Okay, so what do we have here? This is x to the fourth over 2 minus 3x squared plus 3 inverse tangent x from 0 to 2. So, put in our 2 first. So we've got 2 to the fourth, which is 16 over 2, which is 8. 8. There we are. 8 minus 3 times 2 squared, which is 3 times 4, which is 12, plus 3 inverse tangent of 2. Now, if I put the zeros in, I've got 0 minus 0. Now, what's inverse tangent of 0? Right, it's 0, because tangent of 0 is 0. So we don't need this 0. This is basically our answer. So the final answer would be 3 inverse tangent of 2 minus 4. Now, if you were to plug that in a calculator, what would you get? Oh, that's it. They didn't plug it into a calculator. Okay, now if you were going to plug that into a calculator, you would use radians always. Degrees are gone. So this would be in terms of radians. Okay, cruising onward. All right, now, remember, we have no way of getting an integral of a fraction because we don't know how to do the quotient rule in reverse. So what we're going to do is turn this fraction into a series of monomials. So this is going to equal integral from 1 to 9 of 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared dt. Now I could simplify this, so this becomes integral from 1 to 9 of 2 plus square root of t minus, instead of saying square root of t, let's go with t to the 1/2. That's going to make it easier to integrate. And 1 over t squared is t to the negative 2. Okay, so this then becomes 2t plus t to the 3/2 over 3/2. Remember, raise the exponent by 1 and divide by that value. And then we've got minus t to the -1 over -1. And we're evaluating this from 1 to 9. Okay, so let's clean this up a little. So we've got 2t plus, now 3/2 on the bottom make it 2/3 on the top. And then minus the negative becomes plus. T to the -1 is 1 over t. Now, notice the ones, or I should say the lower limit of integration, will matter. If this had been 0, well, if it had been 0, we'd be in trouble because we'd have an undefined term. But now we have to put in the 9s and the 1s and subtract. So when we put in the 9s, we've got 18, 2 times 9, plus 2/3 times 9 to the 3/2. Well, let's just work that out over here. So 9 to the 3/2 equals 9 to the 1/2 cubed. Remember from Algebra 2. 9 to the 1/2 is square root of 9, so this is 3 cubed, which equals 27. So this becomes 2/3 of 27, and that equals 18. Now, plus 1/9. Now, minus, we put the 1s in now. So 2 times 1 is 2. 2/3 times 1 to the 3/2 is just 2/3. And 1 over 1 is 1. So we put the 9s in, we put the 1s in, and we subtract. And so we get 36 and 1/9. Let's just do it like this. 36 and 1/9 minus 3 and 2/3 would be 3 and 6/9. And so this equals, oops, rats. We'll edit that out later. 35 and 10/9 minus 3 and 6/9. Remember back from 5th grade when we had mixed numbers. So 35 minus 3 is 32, and 10 minus 6 is 4/9. 32.4 repeating should be my final answer. And yeah, that's what the book has. So that's happy. Now we could make this an improper fraction, but it's not really worth multiplying 32 times 9 to get that. So, cruising onward. We have a particle. Now the velocity of our particle is t squared minus t minus 6 in meters per second. Now, obviously our particle is in frames. Now we're interested in the displacement and the distance of our particle between 1 and 4 seconds. Now, first of all, I want to show you in general, if you have a curve, let's see, there's our curve. Now, this is the velocity curve. And so what we're saying is this is time here in seconds. And this is velocity in meters per second. if I want distance, then what I'm looking for is the area under the curve. How do I know that? Well, the area under the curve, if I think about the rectangles under this curve, then I have base times height. Well, what are the units of base times height? It's seconds times meters per second. So, meters per second times seconds equals meters. So the area under the velocity curve is distance. So anytime you're given a rate of change, and that's what velocity is, it's a rate of change of distance with respect to time. So anytime I have a rate of change of something with respect to time, and I want not the rate anymore, but the quantity of the thing that changed, then I take the area under the curve, which is basically the integral. So the integral of velocity is distance. See, because the derivative of displacement is velocity. The derivative of displacement is velocity, so that means the integral of velocity is displacement. Integral of velocity is displacement. The area under the velocity curve is the displacement. All right, now, I've been throwing around the term displacement and distance almost interchangeably, and now it's time to talk about the difference between the two. So, displacement, distance. Well, first let's look at our curve. So here is the velocity curve. Velocity is t squared minus t minus 6. And we're interested in it from t equals 1 to t equals 4. Okay, so let's get rid of this. From t equals 1 to t equals 4. Now notice, between t equals 1 and t equals 3, the curve is below the x-axis. And then from t equals 3 to t equals 4, the curve is above the x-axis. So basically from we've got the area from time 1 second to 3 seconds is negative distance, and the time from 3 seconds to 4 seconds is positive distance. Now you can see from looking at this, the red is bigger than the green. So that tells you that this particle was going backward from 1 second to 3 seconds, and then it's going forward from 3 seconds to 4 seconds. And we want to find out, first of all, displacement. Now displacement is just going to be the integral from 1 second to 4 seconds. Bam! And displacement will end up being negative. Now, distance is the absolute value of this. So distance says, take the red, take the green, make them both positive, and add them. So in other words, displacement, if I were to walk, say, 10 feet right, and then 5 feet back to the left, So I went 10 right, 5 left. Now, the right will be positive. So I went, my displacement then would be 10 minus 5 is 5. So I went 5 total feet. Now, distance, though, would be 15. Distance is saying I went 10 feet one way, 5 feet another way, I went 15 total feet. So distance is absolute value, displacement is the net progress. Okay, so let's do this thing. All right, so displacement is merely the integral from 1 to 4 of my velocity. So that equals t cubed over 3 minus t squared over 2 minus 6t. And if this was an indefinite integral, remember it'd be plus c, but it's not, it's from 1 to 4. And so I plug in my 1, or my 4, and I have 64 thirds minus 16 halves, which would be 8, minus 6 times 4 is 24. Minus, put the ones in now, so I have 1/3 minus 1/2 minus 6. Okay, so 64 thirds, how do I do this here? Yeah, -8 minus 24 is -32, and that would be 96 thirds. And that equals -28 thirds. Okay, now over here we have 1/3 minus 1/2 minus 6, so that's 2/6 minus 3/6 is -1/6 minus 6. So this is going to be plus 6 1/6, which would be 37/6. So this equals -56/6 plus 37/6, which equals 19.6 meters per second. So the displacement is -19.6 meters per second. Something has gone awry. What the heck went wrong? Okay. "64 thirds, 16 halves, 24. This is the easy part. How could I screw this up? Yeah, they don't show how they got it. They just have -9/2. All right, so this is -32. -32 times 3 is Now, this is, let's just get rid of all of this then. Okay, so 64 minus 96 is negative 32. Plus, and once again, 37.6. And so this equals negative 64.6 plus 37.6, which equals 27.6. Okay, so that means displacement is negative 27.6, which when I divide by 3, it becomes negative 9/2. So displacement is negative 4.5 meters. So what that showed us is, well, let's finish the distance and then we'll come back and look at it all again. So now the distance is the integral from 1 to 4 of the absolute value of t squared minus t minus 6 dt. Distance is always positive. Now, you need to know where it crosses the x-axis, or in this case the t-axis. So you need to know where it changes from positive to negative. So let's look at that. Okay, where did it go from negative to positive, that is? So what we do is we say, all right, let t squared, wrong color, t squared minus t minus 6 equals 0. We want to set that equal to 0 because we want to find out where it crosses the t-axis. So we're going to factor this, and this becomes t minus 3 times t plus 2 equals 0. So that means t equals 3, or t equals negative 2, which we don't care about. So at t equals 3, that means the velocity equals 0 at this point. So now, what does that mean? That means from t equals 1 to t equals 3, it's negative. Then t equals 3 to t equals 4, it's positive. So what we want to do then is we want to take the integral from 1 to 3 of the negative, well, let's just put a negative out in front of here. And then we go from 3 to 4 of the positive. Notice, since I know it's negative from 1 to 3, the absolute value says make the negative negative. Therefore, it's positive. And then I know it's positive from 3 to 4, so I leave it. So now this becomes, same thing we have here, is going to be t squared, or t cubed over 3 minus t squared over 2 plus, rats, minus 6t. Now notice, the whole thing is negative. So what I'm going to do is I'm going to put the negative here, make that positive, make that positive. And that's from 1 to 3. So notice I just changed the signs of everything. Now here is going to be t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. So we're going to put the 3's in, and we're going to put the 1's in, and we subtract. Then we put the 4's in, and we put the 3's in, and we subtract those. And when we add the 2 up, we end up with 61 over 6. Meters. Which, if we want to make that a fraction, it would be 10 and 1/6, which would be 10.167. So notice the displacement is negative because the majority of the travel here is negative. The distance is positive because distance is red plus green. That's it, game over. All right, one last problem. Take a look at page 410, example 7. Now you notice that we've got the power consumption in the city of San Francisco for a day in September, and that's measured in megawatts. And the time is measured in hours starting at midnight. So here's what we have. Power versus time. Now, what we're asked for is the energy consumption in a day. Now this is similar to what I just showed you with velocity and distance. See, what we have is power versus time. Now, if I take the area under that curve, then what I have is power times time, and power times time is energy. Okay, the integral from 0 to 24 of p of t dt, in other words, the area under this curve from 0 to 24, is the amount of power used in a 24-hour period. Why is that? Because power is the rate of change of energy. So if I have a certain amount of energy, but I expend it at a certain rate, then that's my power. Power is the rate of change of energy. So, the integral from 0 to 24 of p of t dt is the integral from 0 to 24 of e prime of t dt. Now, the integral of the derivative is the original function. So this equals energy at the 24-hour period minus energy at the 0-hour period. So, this is the area under the power curve from t equals 0 to t equals 24. Once again, area equals base times height, which equals time times power, which equals hours times megawatts, which equals megawatt hours. This is energy. If this was velocity and time, then it would be time times velocity, which would be hours times miles per hour, or meters, or kilometers per hour. Hour times kilometers per hour, and you end up with kilometers. So the area under the curve of the rate curve equals the amount. So we're finding out the amount of energy in that 24-hour period by getting the area under the curve. Now it's easy. So now what you notice in the book, Everybody check out page 410. Now, what you see here is we're going to take 12 sub-intervals. In other words, we're going to take 12 rectangles. So the first rectangle is going to be 2 hours wide. And so what we do is we look and see where that curve hits at the middle of our rectangle. So where is it at 1 hour? Well, it's about 440 kilowatt hours. I'm sorry, 440 kilowatts. So 440 kilowatts times delta T, which is 2 hours wide. So we've got 440 times 2, plus the next rectangle goes from 2 to 4. So its midpoint is the third hour. So the power at the third hour is 400. Now the next rectangle goes from 4 to 6. Its midpoint is at 5. So notice how this is working. It's the power at the first hour plus power at third plus power at fifth plus 7th, 9th, 11th, 12th, 13th, 15th, 17th, 19th, 21st, 23rd, all times 2 hours each. And we add up those rectangles and we get the area equaling 15,840, which represent 15,840 megawatt hours. That's it. Have fun with these.